Today is going to be the first day of a two-part course, an introduction to FreeSurfer, covering the fundamentals and also helping you guys analyze a data set from start to finish. And you may ask, why are we doing this course in the first place? Because they do have FreeSurfer courses in Boston about every year or so. And I did go to that about, I think it was, I don't know, eight years ago, a long time ago. And these courses like FreeSurfer, FSL, they're good, but they're also very, very intensive. It's very condensed into a few day period, and they cover a lot of different topics. And here, what I want to do is to supplement some tutorials I have online, which are also condensed into, say, like 5-minute chunks covering certain topics and modules about what you would do with FreeSurfer. And this will expand upon that and try to tie everything together, right? So it's a work in progress, and I hope that it's not just these two courses, these two classes, but that we'll be able to extend it into the next year as well and cover some more advanced topics. But the scope of these first two classes is, one, to give you an overview of what FreeSurfer is, what it does, what the main commands are, and then to help you build a model to analyze your own data set. My assumptions about what you guys know so far are, it's a mixed bag, because I realize there's some people here who may have never used FreeSurfer before, and that's fine. You don't necessarily need to have a background with it to gain something out of this course. We may have people who have used it but don't know a lot about the details, some of the particulars, and you'll also get something out of it. And there may be people who have a fair amount of experience already with FreeSurfer. So I'm assuming that we're a collection of those different types of people. And I'm also assuming that we also have some background with command line syntax, because I'm going to be talking about variables, setting environmental variables, and this isn't an overview of that. I'm assuming you have some background with that. Also, if you have some background with neuroimaging processing, like fMRI data processing, I'll be using some analogies to what goes on in fMRI processing, so that helps as well. It's more common for people, I would say, at least in my experience, to first have a background in fMRI analysis and then go to FreeSurfer analysis, rather than vice versa. Although if you ask somebody at the FreeSurfer HQ, if that's what they start with, they don't really understand why you would go back to collecting volumetric data, which I'll explain why in a second. But those are my assumptions about who you are as the audience. So what you're going to learn here, as we saw on the flyer, in day one, this is FreeSurfer overview, what it does conceptually, and it's supposed to give you a good foundation about what's actually going on when you run recon-all. For a lot of people, recon-all is the only thing that they will learn when they analyze FreeSurfer data. And it depends on your question, because for some things, recon-all is all you need to know. It's very powerful, it has a lot of different sub-steps in it, and the output from it, you can get by with that if just doing comparisons of things like thickness and volume in certain cortical regions is your only goal. But we're going to go a little bit beyond that. We will cover recon-all, how it operates, what are some options which might be useful for you. And I want people to know more about just the basics of it. Then we'll be finishing up with surface-based registration, which is how FreeSurfer is a lot more powerful than the other data packages, as well as how to parallelize recon-all, and a brief introduction to FreeView. All right, so that's what we're covering today. If you know a lot about that, you feel like you have a good grasp on that, then I'm not going to get offended if you leave, because that's most of what we're going to talk about. But day two is going to be covering failure modes, which if say you're an RA, if most of what you're dealing with is trying to repair FreeSurfer data that's been run through recon-all, then this would be a good day to come, because we'll be covering what some of the different failure modes are and how you can address them using FreeSurfer's FreeView application. The other part of that day is going to be covering the group analysis part of it, setting up your models, building contrasts, and then doing ROI analyses. The goal after day 1 and day 2 is to be able to run your own analysis from start to finish and have the tools you need to do so. What I'm going to be doing, in addition to recording all of this and putting it up online so you have it for future reference, is also on my website, andysbrainblog.com, I'll have also the scripts you'll need to run some of the things that we'll be doing so far. I know, it's a shameless plug for it, but honestly, it's going to be, I think, most useful because everything's going to be in one resource. Okay. And there's no ads, at least on the website. Okay. The data set that I want us all to be on the same page with is from a website called openfMRI.org. This is about cannabis users, and it's comparing them to controls at 2 different time points. So there's a baseline, and then there's a follow-up. And I thought this would be interesting because, as far as I know, according to the study, they didn't use FreeSurfer. They used some other voxel-based morphometry package in SPM, I think. So it hasn't been analyzed in FreeSurfer. I don't know what it looks like. I'm currently processing it right now. But it has a lot of things which address different scenarios you might find yourself with FreeSurfer. So first of all, you can compare 2 groups. You can compare controls, and you can compare the cannabis users. They also have, I believe, some individual differences data, which we're very big on that. And you can run correlations between the individual differences data and also the different structural properties. And in addition, there's baseline and there's follow-up. So if you want to run longitudinal analyses, you can do that as well. So it's a good teaching resource for covering all those different scenarios. I'm not going to be covering longitudinal analysis on day 2, but possibly in the future, if there's enough interest, we can cover that as well. Is anybody here doing any longitudinal structural analyses, or if that's a possible option in the future? Yeah, okay, you guys are. Good, so this will be a good one for learning some of the basics of that. All right, so let's begin with our FreeSurfer overview. Why use it in the first place? Why use that instead of something like SPM or AFNI, right? Aside from the fact that you can analyze structural properties pretty accurately. Again, there are different morphometry toolboxes like voxel-based morphometry and SPM, but FreeSurfer, in my opinion, is a lot more powerful. So if we compare this to what we typically get out of the scanner, we have these volumetric data sets, which I like to compare to giant 3D Rubik's Cubes. And all the smaller cubes are the voxels. They're volumetric pixels, and in each voxel you have a different value corresponding to the intensity at that voxel. So things like contrasting white matter and gray matter, or contrasting the amount of activity in one voxel compared to the activity in another voxel. This is the basic structure of how these data sets are formed. But they do have some issues. So these problems with voxels correspond to something called the partial voluming effect. If we have a voxel which bridges 2 distinct anatomical areas, say 2 gyri, which could be one anatomically distinct and also functionally distinct, because these different pieces of cortex they could have different cytoarchitectonic properties, and they could be doing different things functionally, right? If you have a voxel that spans both of those regions, and let's say you run an analysis and you find that that particular voxel is active, it's very hard to determine whether the activity in that voxel is due to, say, the region highlighted in green, the region highlighted in yellow, or it could be a mix of both. With these volumetric data sets, we can't determine what the contribution is from those 2 regions. Like I said, this problem is known as the partial voluming effect. And it's not just for functional data. You can see it for structural data as well. Because if we have a voxel which seems to bridge different tissue types, it's hard to determine how much of that voxel, say, is gray matter, how much is white matter, and how much is cerebrospinal fluid. Volumetric-based packages like VBM, they do their best to try to unpack that, but it's not always that accurate. So what FreeSurfer does is it takes these volumetric data sets, all the data we get off of the scanner, it's going to be in this format, and then it tries to reconstruct a cortical surface from those volumes. In other words, it takes what's fundamentally a three-dimensional grid and it tries to expand it into a two-dimensional surface. And the fundamental difference between these two things is that one is composed of voxels, these squares, let's call them, and the other one is composed of a triangular mesh, if we zoom in on that. So these are called vertices. If you know graph theory, they use the same basic vocabulary as graph theory. The intersections of all these different triangles are called vertices, a vertex for the singular, and the connection between them is called an edge. Vertices and edges are the fundamental building blocks of a two-dimensional surface instead of a three-dimensional surface. And at each one of these vertices, instead of looking at the intensity as you would at a voxel, you can then calculate the volume, the thickness, the area, and the curvature, different structural properties at each one of those vertices. So the way that I like to conceptualize it is, this is what I brought my lunch in today, right? This is basically a two-dimensional surface, right? Don't overthink it. Yeah, there might be a little bit of thickness, but just think of this as a 2D surface. And if this is the cortex of your brain, it's very efficient to compress it. And that's why it has all these curves and gyri and folds within it. And so what FreeSurfer tries to do is it can expand it to different inflation sizes. Eventually, as we'll see, making it entirely flat, but you can still see the wrinkles in this even as I expand it. So it still retains information about the gyri and the sulci and the relative locations between these different groups. Okay, does that make sense? I had that epiphany when I was eating lunch, and I was like, I gotta use this. But really, it's a very good analogy. That's really what it is doing, because the brain, the cortex, it's better conceptualized as a 2D surface rather than simply a bunch of different blocks together. Okay, so here's a brief animation giving you a summary of the FreeSurfer terms that you'll be encountering. So FreeSurfer parcellates the cortex. The cortex is called a parcellation, and then the subcortical structures are segmented. And you'll see those called segmentations, so just to get familiar with the basic terminology. All right, so these segmentations, or parcellations, you can gather different structural data from that, like volume, thickness, whatever you want, and then import that into a statistical software package, like R. So at a fundamental level, that's really all you need to know if, say, you're interested in differences within each of these parcellations or segmentations. Okay, so at a very basic level, that's really all you need to know. So concluding our overview of FreeSurfer, why use it? In my estimation, it's the most sophisticated and widely used morphometry package available. Again, there are other ones out there, but FreeSurfer, at least this is my impression, most people use it for surface-based analyses, as well as structural analyses. So why not use that? Also, fMRI activation follows the cortical surface. So I've been talking about structural properties so far. If you want to know differences between groups or differences between different structures, you can do that. But, as we'll also see, you can look at fMRI activation and map that onto a cortical surface. So if I have an inflated brain right here, these look like boxing gloves, and you can see the different gyri and the sulci, and this is mapping activation onto a surface. So you get a better, more accurate representation of where the activations actually are. Because if you think about it, if you think about what's actually going on in your brain, it probably is going to be hugging the surface. It's not going to be bridging gaps. I don't want to call, well, it is kind of a misrepresentation when you look at it from a voxel because you can't tell exactly where it lies on the surface. And FreeSurfer does allow you to do that. And along with that, you can also integrate this with different packages like AFNI's SUMA. Some of us may have used SUMA to map activity that we found from a volumetric based analysis onto a surface, that's fine. That's more of like an interpolation though. A more sophisticated way to do it, a more accurate way to do it, is to first reconstruct your surface in FreeSurfer, and then Summa integrates with that. And this is something for a future course. But basically what you can do is you can run all your analyses on the surface, as opposed to running it on the volume and then interpolating it onto a surface. You're actually running it on the surface, and that's what Summa does. So if you can see here, these activations in this volume, you can see it both on the volume and on the surface at the same time. Okay. All right, so part number 2. Oh, by the way, another good thing about uploading this is that when it's on YouTube, there will be, what are like those timing markers, right? So that should make it easier to navigate. If you want to go back and say, what was that thing about recon-all? What was that thing about surface-based registration? You can get to those a lot quicker. So I will put those up there. Our second stage is called recon-all. And that does all of the FreeSurfer pre-processing. Like I said, for most people, this may be all you need to know. But there's a lot going on there that I'd like to unpack. So, as you can tell from the name, recon refers to reconstruction because you take this three-dimensional volume and you reconstruct a surface from that. Recon-all has a lot of different processing steps. There are, I think, 31 different ones, and they all do different things. So they do things like motion correction, they do things like registration, intensity normalization, different levels of smoothing and inflating. So many, many different things. And these can be broken up into smaller sub-blocks that we can call upon with auto recon, which I'll be covering in a second. So that's what's all within recon-all. And here's what the basic command looks like. So first, all you need to do is specify an image and a subject name. Is really all you need to do. So within this -s switch or option, I've heard it called different things in Unix, this is the subject ID, which you can specify as anything. You can call that anything you want, really. And then this I switch is going to be your input. Now, this can be different things. It can be in MGZ format, which refers to MGH compressed format. It's kind of like their version of Nifty, right? Because FreeSurfer is developed at MGH, and they made their own data format. But you can input anything. You can input a Nifty file. You can input a compressed Nifty file. You can input an MGZ file. It's really not too picky. They've made it very flexible these days. And these are all placeholders. You can replace these with whatever you want. And then this last switch is all, which means to do all of the pre-processing steps, all 31 of those that I just listed. Now, FreeSurfer may throw an error, okay, in which case those are called hard errors, meaning that recon-all simply fails to complete because maybe you didn't have directory permissions, or maybe there's not enough space for FreeSurfer to write out the output. Okay, those are called hard failures. There are also soft failures where recon-all completes, but it's not necessarily the case that everything was okay, right? Maybe it called some things gray matter that aren't necessarily gray matter, and you got to go back and check it. We're going to cover this more in failure modes because that's a big part of the whole repairing process. If you have a good quality T1 image, and if you're using the most recent version of FreeSurfer, which is version 6, I've found that I need to do very little in terms of repairing the surface. Yeah? But it's still good to have those tools in your toolkit. A couple other options that I always like to include are the Qcache and 3T options. Qcache simply means to smooth the data at different kernels. It's going to cache this, and it's important for use at a later stage when we cover the MRI pre-processing step. So what that's going to do, it's going to smooth your data, like your thickness maps and your volume maps. All the different maps output by Surfer are going to be smoothed at different kernels, which is important if, first of all, you want to increase signal-to-noise ratio, and you want to improve the inter-subject registration. This last flag, the 3T flag, it's something new that I've seen lately. And this is a 3 Tesla specific flag. So if you acquire data from a 3 Tesla scanner, which is, I believe, the majority of scanners doing fMRI research these days, this is an important flag to keep for intensity normalization, because apparently there's some nuances with 3 Tesla scanners which get picked up by this switch and will make your data quality a lot better. So to review all of these 31 steps, like I said, they can be blocked into different chunks. The first 5 steps, for example, deal mainly with the volume itself. So skull stripping it, motion correcting it if you need to, doing the intensity normalization, right? In other words, if you find an error, one of these, say, soft errors, where it looks like recon-all completed, but the skull wasn't stripped appropriately. Either it's stripped way too much and you're losing a lot of cortex, or it didn't strip enough, and for some reason it's starting to think that scalp or skull is gray matter. Then you would go back and you would rerun this with some options that we'll talk about next week and see if it actually fixed the problem. Right? So you don't need to rerun the whole thing, because as I'll point out later, the whole recon-all pipeline takes a very, very long time, which is annoying. It's the major drawback of FreeSurfer. But we'll be talking about how we can get around a lot of those problems by parallelizing it. AutoRecon 2 deals mostly with the smoothing and the inflating on the surface. And then AutoRecon 3 has to do with the registration itself for the group level analyses. Okay. A few other things that you should be aware of when using recon-all are these environmental variables, FreeSurfer Home and subjects dir. FreeSurfer Home is where all the FreeSurfer binaries are stored. It's where all the stuff is that FreeSurfer needs to function and to operate. And this is what it looks like in my terminal, at least. So you can see it has a binaries directory. It has some example data sets. It has some other directories for interfacing with, say, FSL and MATLAB. So that's just a default directory. It gets output, I think, to like applications FreeSurfer. You don't need to mess around with it too much. Just pointing out where it is. And also, do you see that subjects directory highlighted in yellow in the right? That's where the subjects dir variable points to. That's the default output directory for where all the FreeSurfer output goes. So if we take a closer look at that, you're going to find things like FS average in the bottom of that second column there. That's like the template that everything is averaged to. And anything that you process is going to be output in this directory. So you can change it, right? If you want it to be output in a different directory, then you'd simply specify subjects dir to point towards somewhere else, which I find useful. If you don't mind everything cluttering up that single directory, then that's fine too. But it'll make your life easier to make it more organized. The directory structure, once you've finished running FreeSurfer, is going to look something like this. So within subjects dir, whatever you specify that to be, it's going to output the name of the subject that you put in that S flag, that S switch. And here's what it looks like in your command line as well. But notice that we have things like label, MRI, script, stats. Those first 5 ones on the left, those are going to be the ones that you're going to be using the most often. Okay, in particular MRI and surf. So all the volumetric data that it processes when it does like the skull stripping and the intensity normalization and everything else, that's going to be output in MRI. All the different surfaces, which I'll get to in the next few slides, like the peel surface, the inflated surface, the white matter surface, those are all output in the surf directory. And in the scripts directory is going to be output everything that recon-all does. If you need to go back and check what happened with FreeSurfer, if you want to see if it had an error or when it failed to complete, that's where you would go. These last 3, I don't know what they do. I never asked, I've never used them, so I'm sure they're important for something along the line, but I never used them. In case you're wondering, I just don't know. So don't ask me. But within MRI and SURF, that's what you're going to be using the most. All right. I want to cover a few of these steps because I've noticed some differences in some of these pre-processing steps depending on what options you give it. So let's take a look at what I think are the most important ones that you should be familiar with. The first one is intensity normalization. And AFNI does this too sometimes, if you want to do segmentation with AFNI. So if you've used that, it's the same idea. On the left is this orig.mgz file. That's without any pre-processing applied so far. Maybe it's been motion corrected, but it hasn't been intensity normalized yet. And on the right is the T1 image, which has the intensity normalization applied to it. What this tries to do is it tries to make all the white matter more homogeneous and all the gray matter more homogeneous in terms of the intensity. Right? So gray matter may have an intensity value of, arbitrarily picking a number, 90, and white matter might have a number of 110 at each voxel. The reason why this is important is because in certain scanners, well, in all scanners actually, the intensity is going to change a little bit depending on the head position. So just as a function of where the head is relative to certain coils in the scanner, it's going to make certain parts look brighter and certain parts look a little darker, which is why that's important. And it also needs that, first of all, to make a distinction between the gray and white matter, and then to appropriately segment those. Another step is called skull stripping, and once it removes the skull, it's going to call that brainmask.mgz. Sometimes you may have a little bit of dura located on the sides. The best option I found for that is something called a G-cut. If you use that with the auto recon scripts, usually that does a pretty good job of removing the dura. That being said, I haven't had issues with FreeSurfer thinking the dura is, say, gray matter. So, I mean, in any case, you should be, more safe than sorry, and try to remove anything that's not cortex or white matter if you can. So that's the brain mask file. And here is what it is going to do if I get my animation running correctly. Okay. So after it's skull scripted, the next thing it's going to do is going to segment everything in the brain. So it wants to make a clear boundary between gray matter and white matter. And also, it's going to segment each of the different subcortical structures, like putamen, globus pallidus, thalamus. It's going to delineate those as accurately as possible. Okay, so the white matter in the cortex and in this red circle are all of the subcortical structures. And this output file is called aseg.mgz. So I'm just running through all the different outputs, the most important outputs that you'll probably be interacting with at some point, and to give you a sense of what corresponds to what. Because the labeling system isn't clear at first. If this is your first time with FreeSurfer, it takes some time to get adjusted to the whole vocabulary. Now, segmentation needs to be good because what it's going to do next is it's going to make some estimates about where the surface boundaries lie between different tissue types. The most important ones are these. FreeSurfer does a first pass estimate of where the white matter boundary is between the white matter and the gray matter. And that's called the orig, or original surface, like an original guess. I've highlighted that here in yellow. That doesn't get used for calculating your final statistics, but it can be useful for troubleshooting, as we'll see in the soft failure modes next week. What I have traced out in blue is the white matter boundary. That's like a more refined guess about where the white matter boundary is. And then from that, it expands outwards until it hits the edge of the brain, and then it labels that as the peel surface, which I have in red. Okay. So after you have your skull stripped image, you have all the intensity normalized, what FreeSurfer is going to do is it's going to segment everything into white matter, gray matter, and all the subcortical structures. So here's a brief summary of everything that I've just been saying. It first segments the structures into cortex, white matter, and subcortical structures. And this is called aseg.mgz. It's going to zoom in a little bit, and it's going to highlight these different tissue boundaries. So there's the orig, and that's the surface representation on the right. There's the white matter highlighted in blue, and again the surface representation on the right. Those two are pretty similar, orig and white. And then the peel surface, which is a little bit smoother, it gets expanded from the white matter, and then you have your peel surface. Now, the difference in distance between the white matter and the peel, that's what's calculated as your thickness. You can further inflate this, like with that paper bag analogy, into like this boxing glove, and this is the inflated surface. And you do this for both hemispheres. So that can give you a very accurate tracing of where different structural and functional differences are. It gets further inflated into a sphere because we need this for inter-subject registration. This puts them all into the same space with this template located in FS average that I pointed out before. And it aligns the gyri and the sulci along 2 dimensions, latitude and longitude. You can think of these as like planets that are being aligned along hills and valleys. This is then parcellated into, like, based on an atlas, and then mapped back onto each individual surface. These different atlases, you can then calculate things like thickness, volume, all your different structural data according to those parcellations from each atlas. And these parcellations, based on the atlases, they're called annotations. It's another FreeSurfer word to be familiar with. So parcellations, segmentations, and finally annotations. And you have a couple of different options depending on your question. First of all, there's the Dedekind-Kiliani atlas, and you see this labeled with just aparc.annot for annotation. And there's a more fine-grained one called the Deschutes atlas, and that's with the A2009 or 2005. They updated it in 2009. And that has many more parcellations and annotations if you want to use those. So it may, for example, give you a distinction between supramarginal gyrus and angular gyrus, and like different subregions of different parts of the cortex. Okay. So to sum up, the MRI and the surf directories are what you're going to be using the most. And the ones that I just covered in those different slides are the segmentations, the T1 intensity normalized image, the brain mask with all the skull stripped out of it. And in the surface directory, you have the white matter, the peel, and also the inflated and the spherical surfaces as well. Okay. We're going to finish talking about recon-all with the Q-cache and the 3 Tesla commands. As I said, Q-cache smooths your data at different smoothing kernels. So if you don't do any smoothing at all, you can see it's a little bit more jagged around the edges. This is just a random thickness map that I mapped onto the template surface. As you increase the full width half max, you get smoother data maps. And Q-cache will do that in 5 millimeter increments all the way up through 25 millimeters. And this is important because what FreeSurfer has done, why it caches all of this, is it's cached these Monte Carlo simulations about what cluster sizes would be significant given different smoothing kernels. So it saves you a ton of time as opposed to doing that each time that you did a group level analysis. This is already going to be cached, right? So it just makes the whole process a lot easier. And like I said, these are all automatically output with the Q cache option. I want to say a few words about the 3T flag because I've only been using it lately. Intensity normalization without 3T compared to with 3T, I don't know if you can really see the difference. It's a little, the white matter is a little bit brighter with the 3T option, and it also seems to do a little bit better job segmenting the gray matter and the white matter. Again, I haven't seen a huge difference, but if they've included it, it's probably for a good reason, and if you're using a 3 Tesla scanner, you should probably check it out. As far as segmentation, like the subcortical structures, I don't really notice a big difference at all. The only thing I've noticed, and again, just from a few random slices, is that without 3T, it appears to do the estimate of the peel surface a little bit worse than compared to with the 3T option. Again, really not a big difference at all, but every little bit helps, and there's no downside to it as far as I can see, so why not include it? Okay, any questions so far about the basic concept of FreeSurfer or what recon-all does? Anything so far? Okay.
I have a question.
Yeah.
About the Q cache, the smoothing corner size, is it automatically adjusted internally, or should we provide a preset measurement?
Are you asking about whether you need to specify different smoothing levels? Okay, so the question was, with the Q cache option, do you need to specify different smoothing levels? It automatically does it from 0 to 25 at 5 millimeter increments. And those are the tables that FreeSurfer will generate for calculating things like multiple comparison corrections. Because cluster size is going to depend on your cluster forming threshold and also your smoothing parameters. Yeah, so it's all output automatically. I have tried computing my own tables. It's a huge pain in the rear. I don't see why you'd really need to do it. Like, I wanted to know what it would be like with, say, like a 7 millimeter, 8 millimeter smoothing kernel, but there's not a whole lot of point to it. I mean, again, like, I don't use a 25 millimeter smoothing kernel, and I don't use a 0 millimeter smoothing kernel. But it doesn't take that long to generate those maps. It just does it all automatically just in case anybody wants them. So there's not a lot of fine-tuned control, but I have no problem with the defaults that it outputs.
Another question
Yeah.
will be about intensity normalization.
Mm-hmm.
Often we are asking scanner to do normalization itself,
Mm-hmm.
but as we know, HCP does not apply that. They are getting just unnormalized images.
Okay.
So is there anyone who experiment which might be providing better results?
I haven't looked too much at the HCP data. So the question was, let me see if I'm summarizing this correctly. HCP does not do intensity normalization from the scanner. I don't think that's too big of a deal, though, because FreeSurfer will try to do that automatically with their intensity normalization. The data set that I pointed out earlier, the one from OpenFMRI, there are big differences in the amount of intensity, like at the back of the brain compared to the front of the brain. And the intensity normalization from FreeSurfer appears to account for that just fine. So I think that they've been troubleshooting it a lot, and that they've been able to account for anything like that. Yeah. In any case, it seems to be a processing step either with FreeSurfer or something else that you'll need to do after the data is acquired. I'm not sure how scanners have tried to account for intensity inhomogeneity based on coil position. I don't know. Yeah. But with some scanners, it's clearly a lot worse than others. Our scanner's fine, by the way. Fantastic scanners. The best. 3T Siemens. Yeah, we had a Trio, and we're upgrading to a Prisma. Yeah, but the Trio data has been just fine. Very little inhomogenities.
This question is because we need to set whether you output the image without normalization or with normalization.
Oh, I see. Oh, you can specify that.
Once you output the image with normalization, then you're not going to have the unnormalized.
Exactly. I didn't know that.
HCP definitely prefer not to normalize.
Okay. Okay.
So,
Wow, I didn't know that. So just for the audio recording. So apparently you can,
yeah,
from the scanner, you can specify whether you want normalized or non-normalized. What kind of scanner?
Siemens.
A Siemens. Okay. Good to know. Yeah. So what I'm going to say without knowing more about that is I would recommend outputting the non-normalized just because who knows what kind of interpolations the scanner's doing. I don't know. I've been happy with the intensity normalization that FreeSurfer does. All right. Okay, so part number 3, inter-subject registration. This is a fun one. I had a fun time doing this. Volume-based registration, I wanted to do a brief overview of what happens with that because conceptually it's the exact same thing that we're doing with surface-based registration. But surface-based registration appears to be more accurate spatially for determining, again, differences in structural or functional properties. So volume-based registration, if I just take, say, a template image and some other image from my scanner, just a random subject image, and let's deal with just the coronal slice for now. Notice that the template can be very different from the subject, right? Differences in size, differences in intensity, and the whole purpose of registration is to try to match those up as quick as possible. So translations, shifting it a little bit to the right, fine-tuning it, trying to overlay it as well as possible, as well as rotating it. We can zoom it out, make it bigger, or we can make it a little bit smaller to make that registration much more clean. Or we can do shears where you take the opposite corners, like a rectangle, and make it more of like a parallelogram. So these are the linear transformations you can do. There's 12 degrees of freedom, 3 for each of those that I just pointed out. It's called an affine transformation. And that's good for trying to match up like the size and position, but not necessarily the shape, which is important when you're trying to register one surface to another. So what FreeSurfer does is nonlinear transformations, which are much better for this. They're better at matching shape, and unlike linear transformations, you don't need to maintain the relationship between certain points. So what that means is that, like if I'm stretching an image, if I'm doing a linear transformation, if I'm taking this end of my image, I have this invisible square here, I'm taking this end of the image and I'm stretching it out this way, there has to be an equal and opposite stretching going the other way, right? That's what those zooms are doing. With a nonlinear transformation, you can keep one area completely static and say expand one region, right? So imagine, let's say, for example, keeping the ventricles as they are, but inflating or shrinking the gyri as you need to, or modifying one part without having to account for any other part of the image. So not surprisingly, that takes a lot more time. Nonlinear transformations are very time-consuming. You can do it with volumetric data, but again, with voxels, which have these, which can span multiple tissue types, and they haven't had the surface reconstructed with all the magic that FreeSurfer has, it's much harder to precisely match up all the grooves and the curves of the brain. So what the surface-based registration is going to look like is once you've reconstructed the surface and inflated it into spheres, this middle sphere here, this under the B, that's the FS average that all these spherical two-dimensional maps are being registered to. If red is the sulcus and green are the gyri, I think I have those right. Again, think about trying to match up different planets, right? And planets have different topographies. There's hills and there's valleys. And we're trying to do the exact same thing here. We're trying to match these up as closely as possible. Now, FreeSurfer is going to have certain constraints. Things like the central sulcus, the calcarine sulcus, the Sylvian fissure, those are big landmarks. Everybody has them, and those should be the ones you're matching up as well as possible, right? You may need to expand it a little bit, or shrink it, or jiggle it a little bit, but those things should match up. There are other parts of anatomical variability, like things like a paracingoid sulcus. Not everybody has one of those, and that's going to get correspondingly less weighting when it tries to do this registration algorithm. And once it does that, it will map those back out onto each subject. Again, everybody's going to be a little bit different, but the major landmarks are going to be more or less matched up. And smoothing is going to then smooth over a little bit of those intersubject differences, so that, let's say if you have activation in or structural differences in the supramarginal gyrus, and let's say it's a true effect, then that should tend to overlap more with the more smoothing that you do, and you're going to get a correspondingly stronger statistical test with that. Okay, so bottom line is, just like with volumetric analyses, we're trying to find a common group space, just like you would with like a tally rack transformation. FreeSurfer, it does everything in M&I space, in case you were wondering. As far as I know, there's no way to convert from that to tally rack. I think tally rack is kind of on its way out. I mean, I'm not going to miss it. I don't think anybody else will, but just so you know, if you've been using tally rack coordinates, that you got to get adjusted to a new system. I think AFNI's trying to phase it out too, but they're having a devil of a time because all their extensions are, say, tally rack, regardless of where you normalize it to. So that, yeah. Anyway. You know, you've been in the field a long time when you have an opinion about that kind of thing. It's like, dude, who cares? But M&I, I think, is the way of the future. All right, so let's wrap up with parallelizing recon-all. These are some exercises that we'll be going over in the last part of the class today, and also will be up online as well. And I'll direct you to where all this stuff is located. This is something I've been working with recently because, as everybody knows, recon-all takes way too long. FreeSurfer in general is very, very slow. Because of everything that I just mentioned, there's 30 different steps, there's nonlinear transformations, a bunch of stuff is going on. It's going to take a long time for all of that to complete. But at a certain point, too long is too long, right? And it can if it's tying up your machine as well, and it's taking like a week or more, that's a big problem. It's not insignificant. So let's say you have subject 1 and recon-all, depending on your machine specifications, there's a wide range, but about 6 to 24 hours. If you add up all your subjects, and let's say you have a typical data set like 40 subjects or 50 or 60 plus, that's going to be a long time. Okay? Let's say that your machine's on the slower end, 24 hours. And you have 50 subjects, that's 50 days to process one data set. And that's no good. That's unacceptable in my book. So option number 1 is to download the package Parallel. Does anybody use this? It's a really useful package, and it's not complicated to use at all. I'll be providing all the links that you need to install it. Not many steps though. So first you need to install Xcode, the latest version of Xcode, if you're using a Mac. And by the way, I should have specified this up front, but this is mostly for Mac users. This course is geared more towards people who are using a Macintosh. If you're using a Linux machine, that's okay too. A lot of this stuff still applies as well. But for things like Parallel, this is probably going to be more Mac specific, unfortunately. I'll give you another option though. I'm looking at you because I know that you use Linux. You're the only person that maybe there are other people here too, but Luca for sure. And also this package installer called Homebrew. So it's Homebrew is a package installer. Think of packages like libraries, big repositories of commands you can use to run certain processes. So let me give you an example. Let's say that I have 6 subjects in my directory. Okay, so subject 1 anatomical up through subject 6 anatomical. Once you install Parallel, which it's just like a one-line thing. Once you've installed Xcode and Homebrew, it's like brew install Parallel. Again, it'll be at the very end. But once you have that, here's what the command is going to look like. You're going to just list and grab with a wildcard all of your subject names, and then pipe it into Parallel. Specify the number of jobs, and then recon-all. One thing I want you to make sure of is that you're in the bash shell before you use Parallel. It was crashing on me for some reason. I didn't understand why. Turns out it doesn't play well with T shell for whatever reason. That's my default. Other people use bash, and bash is what you need to use for doing Parallel. So you can apply this to however many. Sorry, 1 second. Make sure this runs. Is this running? Okay, here we go. Okay, so first make sure you're in the bash shell. And it doesn't matter how many subjects you have, just make sure that they all have the same extension, say .nai, .naigz. It doesn't matter. I'm also setting this subject dir to be my present working directory, just so I output everything into my current working directory. That's what I was talking about earlier. That's not necessary, but I find it a lot more easy to use. It's a lot easier to be organized. So here's the Parallel command. Again, doesn't matter how many you have, you're grabbing all of them with that ls command, and you're feeding them into Parallel. And I'm giving it the qcache option as well. And I want to unpack what this command is actually doing, regardless of your level of expertise with Unix. This first part of the command, this ls star.nai, that's going to expand into all of these different subject files that I have right here, these .nai files. And then this vertical bar, they also call it a pipe. It's going to be piping all of the output from ls.nai into Parallel. Okay. Jobs 8 depends how many cores you have. I think most laptop Macs have about 8, at least mine does. You may have more, just to speed up the processing for it. And then recon-all. Now, this notation's a little bit weird, but all it means is that these braces mean to specify everything on the left side of that bar. And the dot means to strip the .nai from it. Otherwise, every subject folder would be called the same name as the input, which you don't necessarily want. Once you run that, for me on my machine, this is a MacBook Pro 2011 with 8 cores. I can process maybe 6 subjects a day. A little bit less, maybe. But again, that speeds up your processing by a factor of 6. That's not insignificant at all. And it's also important if, and just to show you that it actually completed, or was actually in the process of completing, the reason that that can be really useful is, let's say, instead of using the next option I'm going to be specifying, using a supercomputer, you just want to rerun a specific part of recon-all. That maybe doesn't take too long. You can run that over all your subjects relatively quickly using that Parallel command. So, very useful command if you're using it on your own individual machine. This next option is using a supercomputer. And I thought about this for a while because I've used a supercomputer in the past. What's that? Build a supercomputer. Just hook up everybody's computer and take them over if you need them. That's one way to use a supercomputer. The first supercomputer I used was at OSU back in the day, and it was very useful, very quick, and I was happy with it. I haven't used a supercomputer here at Yale. Has anybody used a supercomputer at Yale? Or a supercomputer at Amherst? Or yeah, you've used it. You guys have used the Yale supercomputer? Yeah. Yeah, okay. Okay. I haven't used it yet. And I may make a separate document for how to use that specifically with FreeSurfer. But I wanted to make this as generalizable as possible because not everybody may have access to the high performance cluster. You know, like you may not go to Yale, you may not go to OSU, and so different supercomputers I found have, you know, slightly different parameters for what they want people to do when they submit a job. So the one that I found is most applicable is called Open Science Grid. This is funded by NSF, and I just said I want it to be generalizable, but I think you do need to be a U.S. citizen to use it. So I'm sorry, but the point is, anywhere in the U.S. at least, you could be able to use it. And here are the prerequisites, and I don't want to get too far off the beaten path, but I also think these are important things to know because we're increasingly using more shared data, right? We have these open access databases like OpenFMRI, Human Connectome Project, things like that. And I want people to start to be familiar with this. So a big part of this data sharing is first de-identifying your data, right? So stripping away things like age, sex, weight, height, any kind of identifying characteristics. And I found that DICOM to NIFTY, that's my default for converting DICOM files to NIFTY. Super useful. If you don't use it, I highly recommend it. I haven't used anything else really. That automatically de-identifies your data, so you're covered on that if you convert to NIFTY with it. The second one is to anonymize the data by defacing it using a command called MRI deface. What's the... Yeah. It's a thing. And I didn't know this, but apparently from a high quality T1 image, you can actually reconstruct fairly accurately what somebody's face looks like. I don't know how to do that, but it sounds pretty cool. But you can do it, so this is an important data safety issue. And if you deface somebody, it's going to look kind of brutal, but you get rid of their face, right? Looks like somebody had a skateboarding accident or something. Yeah. But so that's the point. It anonymizes the data, and it really doesn't take that long. And I have the steps outlined on my website as well. So after you've downloaded MRI deface, if you choose to go ahead in the future and do this, here are the commands that you'll need to use, which are also on the MRI deface website, which is on the FreeSurfer website. This is the command for defacing an image. And what I like to do, my recommendation if you're going to use MRI deface, which they don't necessarily tell you on the website, is move your MRI deface command to a binaries directory or some kind of path that you're already pointing towards. So my vote is for the FreeSurfer home/bin because that has all the other FreeSurfer commands as well. So, you know, I have commands like MRI converts, recon-all in there, and if I put MRI deface, it's pretty easy to guess where that's going to be as well because I'm using it with a FreeSurfer pipeline. And these GCA files, which deface also needs, I just move those to FreeSurfer home and I call upon them as I need them. Okay. Luckily for us, so this data set that I'm recommending that we use, the anatomical files are already defaced and anonymized. So for this sample data set, you don't need to go through all that. You don't need to go through downloading MRI deface. But if you want to use it with your own data, because OSG, Open Science Grid, wants you to anonymize it, you're going to have to do it. I'm not sure how they check, to be honest, but you know, better safe than sorry. Okay. So in any case, I've written a brief script for you guys if you want to go ahead and use that particular data set, which, you know, we should have maybe 15 minutes at the end here that we can use to download this. And it's great because if you want to use this this supercomputer, you don't even necessarily have to have FreeSurfer installed, I don't believe, because they give you a command that you download. It's called fsurf, and then you could specify an anatomical image and it submits it to the supercomputer. Obviously, when you need to get it back and look at it, you'll need to download and install FreeSurfer, but if you don't have that yet, it shouldn't stop you from getting started on it. All right. So here's the command. Again, this will all be available. You know what? What I'm going to do in our last few minutes is I'll try to put this onto a flash drive and pass these slides around in case anybody wants them. Okay? Because also in the comments box, I have things like, the websites to go to and a few other things which might be useful. So here's the command. It's really just a simple for loop. What this fsurf command does is you specify the subject name. Again, that can be anything. You specify your input, which can have an NII extension, a GZ extension, an MGZ extension. It's all okay. As far as I know, I haven't had any issues with it. Since our data is already defaced and de-identified, you just specify those as flags, and then specify the most recent version of FreeSurfer, which is 6.0.0. It goes ahead and does that, and then you check the status of your workflow by typing fsurf list. Yeah, and the commands for then getting it back off the server, I'll send that along to you guys as well. But really, just it's a one-line command. I'm just wrapping it up in a for loop and doing it for however many subjects that you have. It submits all of them, and in my experience, I just did this with one of my data sets because I wanted to rerun it in Summa, right? So I had to process everything in FreeSurfer, and I wanted to do it in the most recent version of FreeSurfer, just to be up to date. And that took, for everything to be processed on the supercomputer, most of it got done within about a day. For everything to be complete, it took about 3 days. So for example, it was 75% on day 1. Cumulatively, it was 85, 90% day 2, then the last few on day 3. Because you still got to wait in a queue at some point. So this isn't like a silver bullet. It's not going to make everything super fast, and maybe the high performance cluster will be faster in that case. But if you want to offload everything off your machine, process a bunch of subjects, and get it done relatively quickly, I found that this resource is really good, and it doesn't cost anything. Does HCP cost anything? No? Okay. I've heard that using supercomputers... What was that? You have to be a member of the EL community. I see. Okay. So yeah. So this doesn't cost anything either. All right. Okay. So I hope that stuff will help you guys get started. I wanted to end with a brief demonstration of FreeView, which first of all will give you some familiarity with what it does, and also summarize everything that I've said so far about FreeSurfer, recon-all, what the output looks like.